Monday through Friday.
I have seen the face of God.
You just might be right, Mr. Just might be right, Mr.
Ooh, it feels good to play into that again. Good evening, ladies and gentlemen. Good morning, even, I guess we are. After midnight, as it now is, GMT+1. It's Freemanjack on msiradio. And, of course, Scotland is free. Of course, just to start the show, I have to tip my hat to the fabulous people that I have had the great good fortune to meet over the last couple of weeks. I was, of course, up in Preston at our Super Dubs' birthday. Super Dubs is still around. He won't be rejoining me back on the air. He's far too busy basically learning how to be a businessman. But yeah, no, he's still really active on the scene, just no longer putting his head above the parapet. I think he had it battered a few too many times. Yeah, so got to say hi to Frank and the Preston Truth Juice posse. Rusty the Man was there. Wonderful Lebanese legally trained type. I wish I could remember his name. Absolutely eludes me, but spent some fascinating hours in conversation with him. He really had an incredible backstory, and of course not for one moment to forget to mention the fabulous Laurie, who is doing me the grave service of putting up one of my oldest boys while he settles into university up there, and I just can't begin to thank you enough. Thank you so much, Laurie. And of course the lads up there, the Celts north of the border, adopted me as an honorary jock for the weekend and made me feel just so incredibly at home. I honestly felt relaxed at Laurie's for the first time, genuinely, on a molecular basis. Nothing could trouble me. It was wonderful. I thoroughly enjoyed the entire weekend, even regardless of the 14-hour drive that it took to accomplish the round journey. But yeah, a fabulous time, and just have to take my hats off to you all. You're a fine bunch of people. You should all congratulate yourselves and pat yourselves on the back. Okay, well, as you might have gathered, my topic for this evening is my numerical flux and the computational mainframe theory. Let me just pull up my blog here. So my blog, basically, I'll be exploring the potential mechanisms that describe and construct our reality. In a fuller extension of digital reality theory, we'll be delving into the inescapable conclusion that has to be drawn from a universe that appears every day to be more a construct of intelligent design. And does this lead us to the conclusion that we need a God to describe our reality? I'll leave you to draw your own conclusions, but personally, I have been... You'll recognise many of the aspects of the material that I cover tonight if you're a regular listener of mine. I've been exploring many of these elements in isolation and to some degree in collection for some time. Many of you may have heard my interview with Tom Campbell, the great theoretical physicist of digital virtual reality theory. I've recently been working with his colleague Ted Vollers privately. Unfortunately, Ted's vocal cords, due to his huge great age, prevent him from coming onto the radio, which I feel is a great shame. Unfortunately, he can only speak for with any clarity for sort of 5 or 10 minutes at a time, which obviously isn't any way long enough to explore any of these constructs. but I have to again give a big thank you to Ted Vollers. He has been incredibly gentle with me. I presented my numerical flux theory to him on a bit of a wing and a prayer, really, on a bit of a whim. I don't really know quite what I expected to achieve from it. I suppose some sort of either confirmation, or at least perhaps by approaching somebody that I knew wouldn't assume it to be ridiculous and may be able to guide me had I've got it completely wrong, was, I guess, the best that I could hope for when I forwarded it to him and re-contacted him, suggesting that if he thought that I was completely insane or possibly some kind of a deluded stalker, that he was quite welcome to let me down gently with a pat on the back and an off you go, Jack. The reply came and just completely knocked me off my feet. He had taken so long to reply, partially because of obviously the demands on his own time, but also because he had wanted to reply in the most full and considered manner. And the reason for this being that my little 2-page thesis that I had sent him, that I'm about to I'm going to play through an MP3 of it, simply because it's so wordy that it's almost I get tongue-tied just trying to say it out loud. So I pre-recorded it and have edited it for clarity, and I'll play that through in a moment. But I presented him with this 2-page thesis, expecting him just to turn around and go, "No, you're mad." And instead of doing that, he both fully replied to my queries about my thesis, but also pointed to about 50 pages of the MBT wiki, the Tom Campbell Wikipedia that both him and Tom Campbell and Ted Vollers had co-authored, pointing to about 10 years of Tom and Ted's co-authored work on exactly the subject that I had elaborated in this 2-page thesis. Obviously their 50-page 10-year wiki is a more complete examination of the subject. They will both keenly admit that it's a work in progress, that it's not a full theory, that many of these theories really are intellectual voyages, and there is no tangible evidence that you can really point to prove them. So to some degree they're more philosophy than science. So as a result they're always largely a work in process, a matter of refinement. But the thing that really struck Ted, and the thing that I was most taken aback by, was the fact that my little 2-page essay pretty much summed up the larger picture of Tom and Ted's work on the void, on the plenum, but also furthered the theory a little, in as much as it suggests a framework on which the void may be constructed, and how numerically reality can collapse out of what I have described as the numerical flux. Perhaps probably best at this point just simply to play you this little short 6-minute piece. I did play it the other week on air when I was playing Pod Soup, so some of you may have heard a slightly rougher version of this, but this is now the polished version of it. So here we go with numerical flux and the quantum and the computational mainframe. Numerical flux and the computational mainframe. Reality is a digital matrix. This matrix is driven by mathematical logic. It is unlikely this mathematics is derived from base 10, denary, or even binary. The most elegant number system appears to be base 12. In a spherical universe, base 12 has the most concordance. As thinkers in deanery, base 12 presents some difficulties to overcome, not least of which two unique numbers, with which to express the concepts of 10 and 11 in base 12. These two numbers are obsolete concepts in base 12. The use of an 11-beaded abacus avoids the need for this consideration. However, when thinking about the output of any calculation, base 10 thinking must be avoided. Reality is geometric. It has 3 dimensions of space and a direction of time. The initial geometric form is the triangular pyramid, the tetrahedron. It requires the fewest lines and points. Let us examine dimensions, starting with the point. Of course, the point has no area or length. It is theoretical. 2 points define a line, the first dimension. A line has length, but no thickness. It is theoretical. 3 points describe a triangle, the first 2-dimensional object. It has length and width, but no height. It is theoretical. 4 points make a tetrahedron, a triangular pyramid, the first platonic solid, the primary 3D object. Reality, at last. Time can be thought of as the change of state or rotation through the other 3 dimensions. Now let us consider the topography, the shapes of surface. Largely, we only see flat surfaces, but this is a deception of scale. We live on the curving surface of a sphere. As a result, apparently vertical parallel walls of a building are in reality 2 divergent lines whose common source is the Earth's centre. Subsequently, concepts such as up and down would be more accurately described as out and in. Indeed, it is a reasonable model to use quadrants of a hemisphere as a basis of all geometric considerations. A quadrant of a hemisphere is a tetrahedron. It is therefore reasonable to model reality in a tetrahedral grid. Human mathematics is linear and largely lateral or one-dimensional. There is no reason to assume that the same is true of the mathematics of reality. Indeed, if the mathematics of reality use the same economy of form that geometries use, then we might consider attempting to use tetrahedral maths, with each point being an input or product and each line being an algebraic equation. Any input of data at any point would simultaneously, relativistically, alter the condition and product of every interconnected point. This would produce radiant waves of interpolated fields of number. It is entirely possible that we live in a polarized reality, one in which we can only observe, let's say, horizontally polarized matter. We could live in complete ignorance of anti- or vertical reality, as our senses and scientific equipment are all made of the same horizontally polarized matter. This polarization would suggest star tetrahedral geometry. A pair of tetrahedra inserted through one another, the upper point of one extending through the base of the second. If data or energy is inserted into this symmetrical polarized system, the resultant energy field would be a double torus with energy flowing and returning in both outward and inward streams. If extended to the subatomic realm, this might explain observations such as electrical polarity and up and down spin. If reality is digital and virtual, then its very construction must be numerical. At the atomic scale, we see a constant state of flux. I feel this is the closest direct representation of what may be happening at the numerical or computational level. Assuming that time runs more or less in a linear flow as we tend to observe it, then the evidence of some sort of expansion appears to be visible. It is my suggestion that in some primordial universe, that number and numerical interplay was all that existed. Due to the eternal churning flux of these computational numerical interactions, sequential strings of numbers would eventually occur. Initially, these sequences would be incoherent and unstable and result in no evolution. However, over eternities, successfully adaptive algebraic interactions would collapse out of the general background flux. Initially, I see these numerical sequences being most likely linear or two-dimensional, a numeric neural network eventually. Interconnected algebraic sequences could then, again given time, express every possible numerical value in either linear or two-dimensional form. A calculable number of iterations would accomplish this. Having filled the available computational space, the same evolutionary pressure would eventually force a fractal Mobius pinch point, expressing all of the computational complexity of the 1 or 2D into this new third dimension, but without occupying any of its volume. I feel this is how reality came into self-realized existence without the need for deity, driven only by the fluid interactions of number and the evolutionary pressure driven only by nature's bias towards the successful and against the obsolete. This is one clear law of nature. In conclusion, reality is a novelty factory, and we are novelty factory assembly workers. Our nature is to create a lot of novelty and complexity. It strikes me that this, in and of itself, is enough. The stars shine no more dimly for me than for you. Right, so I'm going to have to kind of leave it to you guys to forward any questions to me if there's anything that kind of struck you while you were listening to that. I don't know if it went kind of straight over your heads or if it struck you as just entirely bonkers. But I suppose really I need to endeavour to explain why it's important. Now, for me, digital virtual reality theory goes a long way to providing a suitable model with which to describe the world in which we live in, a much more acceptable model than the one that we're given through the SI model, the standard scientific unit model. While I find it very satisfying as a theory scientifically for the obvious, the standard issues that face us in science, I also feel that it goes so much further than that, and that as I'm finding across fields is that many of the world's respected scientists, some of the theoretical scientists, some of the hard real world scientists are finding that they're coming to inescapable conclusions through their researches and their experiments, and that those inescapable conclusions would lead the God-bothering, the fearful, the unimaginative to have to refer back to some means of deity, some beardy white guy in a cloud to have created the structure from which this digital virtual reality would need to be constructed. And so, having found an elegant model that explains reality without the need for deity in its complexities, it refers back again to this omnipresent intelligent design argument, which has to be confronted if we are to live in a world where there are no gods or demons, if we are to live in a reality where consciousness truly is sovereign and we do not have to refer to some greater being other than the force of nature itself, which to some degree would by primitive cultures have been quite rightly referred to as deity, but only in as much as the biosphere appears to be an organism much like ourselves, with cells that accomplish various tasks and organs through which various mediums flow, be they liquid or gas or mineral. And so in that respect the biosphere is the only, the biosphere and the larger universe to me are the only true sort of deity in any great sense, in as much as they are something greater than ourselves. but I don't feel that they are necessarily an intelligent deity. What I feel is that many of these scientists are coming to the inescapable conclusion that the universe is driven by an algorithmical, arithmetical code, and that in the understanding of this, the nature of this code, I have begun to see the reason why I found the various significances that I found when I examined numerology. I can understand the significances that I saw when I examined geometry. I found the same significances when I examined algebra, when I examined astronomy, when I examined sociology. And here's a point, I think it was actually our Donegal, or I may be corrected, it may have been our Johnny, who possibly said that politics can be derived from sociology, sociology can be derived from biology, biology can be derived from chemistry, chemistry can be derived from physics, and physics is derived from maths. Maths is the underlying language of reality. And never a truer word was said without necessarily needing the abstracts of number, of human numbering systems. The number crunching computational capacity of reality is undeniable. And I'm going to play you through a few little augmenting pieces just to kind of give you a feel for what some of the sort of hard scientists are saying on this subject. Here's one. I'm going to put the links up in the chat when I play these through, so you'll actually be able to watch the videos, because some of these, there are some images with them. If you can be bothered to click on the links, I've set them up to run consecutively with what I'm playing over the stream. So if you click on the link, pretty much as soon as I drop it in, within 20 seconds or so, we'll be sort of on the same page. If not, you can listen to it over the stream. There's nothing there that really needs to be seen, so don't worry about the links in the chat if that's difficult with your internet connection or is going to distract from the subject. You'll be able to get everything that you need from the audio only. Right, as you know, I'm on my new setup here, so I don't know quite how this is going to work. I'm going to open the aux channel and hope it doesn't make any nasty noises for you, and go to the first video and copy and paste you the link from it. Right, I think we're going to go with where are we? We've got James Gates. This is from the Isaac Asimov Memorial Lecture. I think it's the 2011 lecture. It may be earlier, but essentially it's a panel of theoretical and particle physicists speaking to an audience of physicists and student physicists. And James Gates is a theoretical physicist working largely in quantum physics, and I think it's Nigel deGrasse, the compere. He's one of those awful who's that British guy that gets everywhere? Oh God, Cox, Brian bloody Cox. He's the American Brian Cox. He's the nice, smiley public face of physics who gives the standard SI version of everything everywhere and never digresses, diverts, or considers any new ground. And I'm really not entirely sure. He's so dismissive in the way that he both poses the question to Jim Gates, and at the end of this piece you'll hear him jump to another speaker who offers any possibility to suggest that what this first chap, what Jim Gates is saying, could possibly be wrong. But anyway, here's the piece, and I'll drop you the link in the chat. I can't hear anything.
You asked that.
I'm asking you that here and now. It's New York City. It's March 7th.
Well, partly it's taken to these very strange images that are behind your head right now. These are pictures of equations. I've been, for the last 15 years, trying to answer the kinds of questions that my colleagues have been raising. And what I've come to understand is that there are these incredible pictures that contain all the information of a set of equations that are related to string theory. And it's even more bizarre than that, because when you then try to understand these pictures, you find out that buried in them are computer codes, just like the type that you find in a browser when you go surf the web. And so I'm left with the puzzle of trying to figure out whether I live in the matrix or not.
Wait, you're blowing my mind at this moment. So you're saying, are you saying your attempt to understand the fundamental operations of nature leads you to a set of equations that are indistinguishable from the equations that drive search engines and browsers on our computers?
That is correct. So,
wait, I have to just be silent for a minute here. So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
Into the equations that we want to use to describe the cosmos, yes.
Computer code.
Computer code, strings of bits of ones and zeros.
It's not just sort of resembles computer code. You're saying it is computer code.
It's not even just is computer code. It's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s. That's what we find very, very deeply inside the equations that occur in string theory and in general in systems that we say are supersymmetric.
Okay. Time to go home, I think. I mean, where are we going to go at? So are you saying we are all just, there's some entity that programmed the universe and we're just expressions of their code?
Well, I didn't say that. Some of those
like the Matrix? That's what you said.
Some of those codes are showing on the screen behind you right now. They don't look like codes, but these pictures, which we call adinkras, are graphical representations of sets of equations that are based on codes. So this is, in fact, to answer your question more directly, I have, in my life, come to a very strange place because I never expected that the movie The Matrix might be an accurate representation of the place in which I live.
Jim, may I give you an argument that we don't live in the Matrix?
Please. Yeah.
A very simple argument.
Give me one now, quick.
A very simple argument.
Yeah, and then Nigel deGrasse goes on to completely fudge over what is possibly one of the greatest revelations from a physicist ever made publicly. I mean, you can tell from the man's grave discomfort at announcing this to such a broad audience that he already knows how this just isn't going to fit with their paradigm. And you can hear from the nervous laughter not only of the panel, the discussion panel, this so-called assemblage of physicists, of scientists, of men of science, but also from the audience. And it's in order to be able to encompass this concept, they would have to shrug off their entire paradigm, everything that they'd ever learnt to be true, everything that they'd acquired, their grave qualifications and their mortarboards and their capes, would all be a futile waste of time, dabbling in the dark. So you can see how mainstream scientists are stumbling upon this almost haphazardly, when essentially what Jim Gates there was saying was that in the mathematics of quantum physics, in order to get the quantum physics to work. Now, bearing in mind that we know that it works, quantum physics is something that is applied. Your processor in your computer relies on quantum physics working. Okay, so the maths for quantum physics is something that is applied maths. Okay, so within the applied maths of quantum physics, when you delve deeply enough into the maths, there is strings of number, and these strings of number are not simply random sequences of number. These strings of number are a binary code, and should you take this binary code and actually put it into a computer and run it as if it were an exe or whatever the Mac equivalent is, an executable file, it produces these beautiful pictures, these stunning fractal mandalas, and you know what I mean, as you can see, the immediate assumption that the compere made there was that this must be evidence of the hand of God. And this is really where my theory, you know what I mean, has to stand the test, where, you know what I mean, where for me I cannot accept the necessity for deity in order to explain the world in which I live. And to his credit, Jim Gates there is incredibly uncomfortable with the suggestion that this is somehow a rationalisation for the existence of deity. I asked for questions. Donegal has presented me. Donegal is actually, I must give him credit here, it was actually our middle of the night, I won't even say late night, it was like early hours AM chats when he was out in the Far East that actually prompted all of this. In fact, that Numerical Flux thesis was in fact written as show notes, which I was going to send to Donegal for the show that I did with him. So again, more credit to you, mate. You dragged this out of me. Again, this is the beauty of the trivium of utilising logic, grammar, and rhetoric in a triangle, in a reciprocal triangle. That when you think of something and apply logic to it, apply reason to it, and then you say it out loud, and then you consider what you've just said, it becomes a feedback loop in and of itself, where an idea becomes refined and becomes more elegant. And yeah, absolutely, through our conversations, through our chats on the MSI chat box in private, most of this kind of came out through the sort of evenings. Yes, and Donegal just asked me a question privately, PM'd me a question, just to explain this, let me just, in fact, read you out his question. It would probably be easier for me as well. Okay. Yeah, he's asked me to explain the relationship between the structures on the quantum scale and the mathematic code, which is the building blocks of these shapes. Well, in the body of the text there, I explained how physical reality is most likely tetrahedral, and we tend to think in cubic structures to some degree. Cubic drawing and cubic design is part of the way in which we can visualize things in 3 dimensions on a 2-dimensional plane. If we draw something, a house on a sheet of paper, we're drawing a 3-dimensional object on a 2-dimensional object, and to some degree our thinking has been very much limited by this 2-dimensional nature of the materials that we use to explore our ideas through. And one of the key things about this glorious age of computerization is that we can now explore. I'll let Stephen Wolfram explain it far better than I can in a moment. So the structure is tetrahedral. The structure is possibly star tetrahedral. Certainly for me, this polarized star tetrahedral structure, where essentially you have a visible, let's say, upward pointing tetrahedron and an invisible, oppositely polarized downward pointing tetrahedron, both of which are effectively connected to infinitely large or small quanta of space, discrete areas of space, each of which is equally tetrahedral in a vertical or inverted polarity. And that with this tetrahedral, I mean, essentially the virtual reality simulations that you watch on your computer, the construction of the hills and the valleys and the trees and the rivers are all constructed on a tetrahedral lattice. Generally speaking, it's triangular, again because of this rendering of 3 dimensions into 2 dimensions. But for things like the new 3D movies, that triangular lattice is now a tetrahedral lattice. So in order to generate the 3rd dimension visually in a holographic virtual reality, i.e. your 3D glasses that you go and sit at the cinema and watch Avatar or whatever through, this is done through a 3-dimensional tetrahedral lattice. And it's in fact the reducing of each of those tetrahedrons into smaller and smaller tetrahedrons. This is one of the things that when I say that the tetrahedron is the basic unit of geometry, if you cut any piece off of a tetrahedron, if you slice a tetrahedron in half, you end up with a tetrahedron. It's irreducible, and the tetrahedron is remarkable because it is the only irreducible 3-dimensional shape, and as such is probably the fundamental shape of reality. But like I say, because of the limitations of us having worked historically with pen on paper as a 2-dimensional framework with which to base our thinking, we have been largely constricted to cubic thinking, box-shaped thinking, because of the difficulties of working with spheres and with angular geometries. Right, okay, well let's just let's augment this a little more. I suppose I better give you a bit of an ear roll break. Where are we? Blimey, we're already an hour in. Okay, well, in that case I'm going to give you an ear roll break and whack on a tune, and then we'll be coming back with, what are we going to do? We're going to go with computational complexity with Stephen Wolfram. Stephen Wolfram, again, my thinking has been driven, I have to take my hat off to, obviously, the genius Buckminster Fuller, the inventor of the geodesic dome, complete genius, probably so far ahead of the curve that it's probably only now, as modern viewers of his work during his lifetime, that we can actually get it in any meaningful sense. I would suggest that most of his audience are simply sitting in stunned awe of him and really don't have the slightest clue as to what the man's talking about. It takes me the most extreme of concentration to make head or tails of what the man's talking about, but when you do, boy, he's out there. I mean, he's just got a completely different view of reality to what any of the rest of us have. Buckminster Fuller, go look him up. My avatar, by the way, the lattice grid that you see on my name on the left there, that's actually carbon-60, the carbon-60 atom, which Buckminster Fuller predicted purely by understanding the geometric nature of the carbon atom and predicting all of its various forms. Hey, Mahatma, keeping it real. Yeah, so Buckminster, the great Buckminster Fuller, Stephen Wolfram, unfortunately has pursued the corporate money-making side of his genius and has created Mathematica and Wolfram Alpha, which are both corporate sponsored products, but possibly some of the few kind of corporate sponsored products that are going to hugely benefit mankind. Wolfram Alpha is a mathematical and analytical tool which is available for business, and Mathematica is an online tool with which you can ask real-world questions of a Google-like search engine, and this Google-like search engine will derive and calculate the maths for you, and indeed, if need be, generate three-dimensional holographic or virtual reality models of exactly the question that you're asking of it. Fantastic piece of intellectual property. It's a shame it's not free. Some parts of it are free, certainly free to universities and students, but mostly you'd have to pay to use it. Yes, but he also did a vast body of work on a new kind of science, and that's the next little 10-minute piece that I'm going to play of Stephen Wolfram was lifted from a 3-part short piece, short lecture by him about the 3 aspects of his work, and it's a nice concise little 10-minute sort of vox of exactly how broad-reaching, how far-reaching the conclusions that have to be drawn from the cellular automata and the process fractals that have only now been able to be explored, although they've been known about for hundreds of years, to actually have the computational capacity with which to run the number of iterations with which to be able to see anything of significance from them. It's literally something that's only been available for 10 or 15 years, largely. Some of the earlier process fractal work and stuff was able to be run on a very basic mode, but certainly in order to be able to run all of the computational space in order to be able to see anything of significance, it really is a very modern thing. So this, when he describes this as a new kind of science, he's really not joking in the slightest. So what have we got here? Yeah, so there's this one. Okay, once again, I'll post the YouTube link in the chat with the right time on it. Right, so what have I got to do here? I need to open that first this time. Right, so see you after the pod then.
Actually, a lot of this is connected to a big direction in science that I was interested in, that actually was the thing that caused me to start developing Mathematica and so on. And it's also something that's sort of very fundamental to the idea of computation. So let me talk a little bit about the science that I've been interested in. So kind of the starting point is, how do you understand, for example, the natural world? Well, 300 years ago, there was this big idea from Newton and people like that we can use mathematical equations as a way to describe the natural world. And that's been a very successful paradigm. It's brought us most of modern science. It's brought us all sorts of engineering and so on. I got interested in what one can do to sort of generalize that paradigm. And what I realized was that you can go beyond kind of the rules that are defined in mathematical equations and sort of deal with arbitrary kinds of rules of the sort that exist in things like programs. So then a question is, well, what kinds of programs might nature actually use? It's probably not going to use the kinds of programs that we write for particular purposes that are thousands or millions of lines long. It's probably just going to use very simple programs. So then there's sort of the basic science question, what do simple programs typically do? So quite a few years ago now, I tried to start answering that question, and I looked at some very, very simple programs. So here's an example. It's a thing called the Cellular Automaton. It's just got cells that are either black or white, and then at each step, the color of a cell is determined by the colors of the cells above it, and there's a simple rule. Effectively, the thing at the bottom there is the program for generating this pattern. Well, you can try different programs, and you get slightly different patterns. Here's another simple program, corresponding simple pattern. Slightly different program, you get a slightly more elaborate pattern. Continue that, running that program for a while, you get this fine, rather intricate, nested pattern. It's intricate, but it's still extremely regular. So a question is, if you look out into the sort of computational universe of possible programs, does everything work like this? Does everything sort of have the property that with a simple enough program, the behavior that you get is somehow has a certain kind of regularity that reflects the simplicity of the program? Well, you can do an experiment. You can just look in the space of possible programs and see what all of them do. And you sort of turn a computational telescope out into this computational universe and see what's out there. Well, you see all kinds of different things happen. Each one of these pictures is a different program. My all-time favorite is Rule 30. And if we look at in more detail at what Rule 30 does, here's what it looks like just starting from a single black cell at the top. We continue it a little longer. This is what we get. So you can see there's a certain amount of regularity over on the left. But this is a pretty complicated picture. And one might, when I first saw this, I kind of assumed, well, there's such a simple rule, there must be some hidden regularity that I'm not seeing. But a few years later, and lots of math and computer science and cryptanalysis and so on later, I realized, no, this is actually a fundamental phenomenon, that even though the rule for this system is very simple, the behavior that it produces can be very complicated. And it turns out that that idea is something that is very robust, very general. It's a very common phenomenon in this computational universe of possible programs. And it's something that is important in understanding, for example, the natural world. There are lots of kinds of systems in nature. You know, you take a snowflake or something, you can find that there's a very simple program that governs the overall structure of the snowflake. You look, for example, at systems in biology. You can find the same kinds of thing. You look at the mollusk shells, for example, you see all the elaborate patterns that they make. Turns out that those, again, can be described by these very simple programs. In fact, you can even be more ambitious than that. You can say, it's sort of a thing which changes one's worldview, one's paradigm about how things work, that even a very simple program that you sort of find at random in the computational universe can produce extremely rich and complex behavior. And that's something that it kind of goes against our everyday intuition, because our everyday intuition comes from things like engineering, where it usually takes us a lot of effort to make something complicated. Here in this computational universe, where we're sort of free of the constraints of sort of the history of human engineering, we're able to very easily produce very complex things, and that seems to be kind of the secret that nature uses to do that. So an obvious kind of big question would be, okay, if that's sort of happening all around nature, what about our whole universe? Is it possible that our whole universe comes from some very simple rule that can be could be found in this computational universe of possible universes? So let's see if I can show you a picture of that. So one of the things one realizes if one's going to actually have a very simple rule that governs the whole universe is that rule has to sort of operate underneath the level of things like space and time and the other things that are familiar to us. And so a reasonable hypothesis, and sort of its equivalent to other ones, is to start with sort of a universe where all there is a bunch of nodes connected together in a big network, and sort of what emerges in a very large scale is the structure of space and so on that we're familiar with. And so one of the things that one can do is to ask, to sort of look at this computational universe of possible universes constructed in this way and see, do any of them sort of correspond to our actual universe? And a lot of them sort of obviously don't correspond to our actual universe. But the interesting thing is that even among the fairly early numbers of possible sort of universes in this computational universe are things which are quite possibly actually our universe out lurking. So that will be an exciting thing if it turns out that sort of out in this computational universe of possible simple programs, there's actually the program for our whole universe, and that will sort of be an exciting moment in science and so on. One of the things that comes out from this is sort of that's an endpoint of science, but one can also use this sort of idea of the computational universe for technology. And perhaps the most interesting thing there is to kind of search the computational universe, mine the computational universe for things that are useful for technology. I mean, we're used in the physical world to going out and finding studying, liquid crystals or ferrimagnetic materials or something like that, and then discovering that we can harness those particular physical systems for our technological purposes. Well, you can do the same kind of thing in the computational universe, harnessing things that you find, sort of algorithmic structures that you find in the computational universe, and using them for practical technology. And in fact, we do this all the time. In building algorithms in the Wolfram language, particularly in Wolfram Alpha, we're often doing this kind of algorithm discovery, saying we need an algorithm that does such and such a thing, then go search a trillion algorithms in this computational universe to find one that satisfies the constraints that we're looking for. So that's that's been a thing that is sort of a very powerful idea in creating, in sort of being able to discover algorithms. We're used to, as humans, we're used to engineering things sort of step by step, figuring out what's true, and setting up our engineering structures by sort of building them incrementally, whether it's us doing it as engineers, whether it's natural selection, kind of progressively, incrementally changing some feature of a creature to make the next one. What happens when you go out into this computational universe of all possibilities is you get to discover all kinds of things that you never anticipated were there. You get to discover a lot of very sort of clever things that we never imagined. There's a lot of implications of going and looking at this computational universe of possibilities. It kind of changes the economics of creativity. It means that you can kind of mass customize things by just going out into this computational universe and finding things which are structures and objects which are useful for particular purposes. And so this has been done quite a bit in art, music, and so on. It's also, as I say, very, very useful in all kinds of technology. It's also useful for creating structures of things. And, for example, one direction that's emerging these days is for things like algorithmic drugs, molecular computers, and so on. Being able to sort of go to this computational universe of possibilities and identify things which one had not anticipated were there.
Before that, we had Stephen Wolfram explaining his new kind of science. If you'd been watching the video there, one of the things that he was explaining is how you don't need numbers to do this stuff. The mathematics that he was describing there are derived from a rule set that don't actually rely on numbers. You have a symbolic representation of black and white squares in a 4-square grid, which is your bit, I guess, or it would be a nibble. Indeed, it would be half a bit. A bit being 8 digits, and the usual mathematical symbols to indicate a process, a function of add, subtract, divide, whatever you. And that by replacing the numbers that you would normally use in maths with these four square boxes with either a black or a white square in each to represent a symbolic, not even a number, but a symbolic representation of a physical space. And through this you can derive all of these natural, apparently biological shapes, and you can model what have largely been exclusively biological systems. Indeed, the Game of Life is a famous one of these, where the computer programmer who programmed this particular little program, when the program was run, instead of carrying out the oppositional behaviour that was programmed in as the rule set for this particular little process fractal, that indeed the units on the screen managed to figure out a way of collaborating and essentially escaping off of the screen. And apparently he saw this result on the screen, having left the thing running sort of unattended, when he came back to turn it off at the end of the day, expecting the usual sort of boring average results, and he was so alarmed at seeing these little black and white dots having collaborated and shimmied off the screen and not cancelled each other out or essentially killed each other, that he really didn't want to turn the computer off, that he realised that what it essentially was seeing was electronic biology, electronic evolution. And this is I have to argue against the evils of the internet. A lot of the time, many people seem to think that the internet is somehow a harmful or a damaging or a dangerous thing. And one of the reasons why all of this fascinates me so much is that I genuinely believe that the internet is a new form of biology. In exploring the regions of this particular theory, it would suggest that complexity ever how can I put this? Nested dimensions being explored. So once you have the 3 dimensions of space and the one of time, whatever dimensions are required to create a further iteration of complexification, that it has to be within one of the 4 dimensions that already exist. So I would suggest that something like light and dark would be one of those. It's most certainly something that could be considered a dimension. It's a measurable difference between 2 points. You can say that this point is bright and this point is dim. You can measure the difference between those points, and yet that dimension exists entirely within the 3 dimensions of space and the one of time. And it strikes me that biology has more or less run the computational space of cellular biology, and as a result it created a new dimension. It created the realm of the technological, and that within that new realm of the technological space, that it created the structure that we now know as the internet. And if the structure that we know as the internet is a biological form, then each of us as computer users, as internet users, become essentially a synapse on the largest neural network ever to have existed in the universe. We have constructed and are all utilising the largest brain ever to have thought, ever to have had a unique idea. And of course this would be completely impossible if that internet was only constructed of the technological devices, the computer hardware and the network infrastructure. It wouldn't have been able to have that unique novel idea. It wouldn't have created any more complexity. It had to interface with biology in order to create more complexity. So the internet is completely without purpose in and of itself. All of the computer terminals, everything, completely facile. But you add biology in as a node on the end of each one of those wire connections, and suddenly we see an entirely new form of biology that the universe has never seen before. I know that many people disagree with me on this, but I genuinely think that if we are in an evolutionary universe, that it is likely to have been evolving from every point independently at exactly the same or nominally the same pace, in which case even if there are other species on other planets, they are likely to only have developed to exactly the same stage as we are. Certainly that would be roughly upheld in what we see with the stars that we can observe in our local cluster of galaxies. They certainly seem to be more or less as evolved as the stars of our galaxy. So, I mean, we're looking at a local region of the universe, which is where any aliens or bloody extraterrestrials are ever going to come from or spawn from. That all appears to be of roughly the same age, and so would appear to be following the same process fractal. Okay, let's just have a quick look in the chat, make sure you lot aren't asking me any questions. Alright, what have we got here? Yeah, again, Donegal's very astute that this, I don't know that this has been hidden from us to any grave degree. I think to some degree the significance of this is the thing that comes out through the Stephen Wolfram and that, is that the significance of this is so novel that I genuinely, certainly with digital virtual reality theory, it seems to be one of the few scientific theories out there that has very few detractors and certainly no overarching disinformation sources that most of the pioneers in the virtual reality theory realm appear to be doing so incredibly tentatively and largely quite privately. So don't expect this on, you know what I mean, your mainstream news or on any episode of Horizon. Although, saying that, give it its due, PBS did do an entire programme on Is the Universe a Hologram? They obviously didn't explore the further reaches of it like this, but they certainly were presenting the double slit experiment considerations and much of the other sort of quantum discovery driven science that is suggesting on a fundamental level that the stuff and substance of reality isn't very real. And this is my point really, is that if we're existing in a virtual reality, if we're existing in a holographic reality, then that hologram has to be generated from somewhere. The structures that are presented by that hologram have to be computed somewhere. And for me, that kind of left me with the kind of part in the Matrix movie where he finally finds the guy who created the Matrix, and it's the beardy guy in the room with all the screens. And I think I don't see any goddamn beardy guy in a room with any screens. There has to be a reasonable, rational, logical explanation as to how we derive this reality which we arrive at. And for me, this tetrahedral grid is the explanation for that, and the action of process fractals in 3 dimensions operating through that tetrahedral grid, or that star tetrahedral grid, is the explanation of exactly what I was seeking in my explorations of fractal geometry and of mandalas and of all of these various structures that Fibonacci, that I had seen in the natural world and through the psychedelic experience and various other experiences that simply weren't adequately explained through the current model. And for me, the resonance of an algorithmic, interconnected, mathematical tetrahedron would radiate out like the ripples in a pond where you drop pebbles in. If you can imagine each of the points of the tetrahedron being a virtual pebble dropped into a three-dimensional pond again. You know, I mean, we have to think when we think about waves, we think in 2 dimensions because it's the only place that we've seen waves propagate. Whereas indeed the hologram that we experience is in fact a 3-dimensional wave function. So the rings propagating into the 3-dimensional pool of reality, into the ether of reality, propagate in 360 degrees by 360 degrees in all directions simultaneously. And it's the interaction, the wave function, what's it called? The beneficial and detrimental interaction of wave fronts and wave troughs, where 2 wave troughs will create a deeper trough, 2 wave crests will create a taller crest, and a trough and a crest will cancel each other out and will leave a flat surface. And if you actually drop 2 pebbles into a pond and watch these 2-dimensional ripples spread out, then where the 2 sets of ripples interact, where they cross, you'll actually see radiant patterns similar to a mandala, similar to fractal geometries radiating out. And this is also representative of the double slit experiment, in one of the fundamental experiments that drove the quantum revolution. That it's all to do with these interference patterns. Well, again, these interference patterns have been studied at great length, but they've all been studied in 2 dimensions, because the limitations of the human eye only being able to distinguish a wave in between 2 discrete surfaces, we are left with only being able to realistically perceive a 2-dimensional wave. Whereas now, in the computational world that we have at our fingertips, we can actually quite literally generate the visual representation of these 3-dimensional waves. And so if you have a 4-noded tetrahedral resonant geometry, mathematical geometry, with which each point interrelates with each other point, and any change made on any of the points will immediately, through its algorithmic connection, have a direct and relativistic effect on its immediate neighbour, and so to its immediate neighbour, and that these changes will ripple through the structure. And if that structure was connected to more and more tetrahedra in a tetrahedral grid, then that these ripples would permeate through this grid, and that the interference patterns created 3-dimensionally between the interaction of these waves is actually what constructs the 3-dimensional hologram that we all walk around in. It's the only reasonable explanation for it. It's certainly the only reasonable explanation that I can come up with. And again, I kind of understood the necessity of all of these parts. I understood the necessity of the interpolated tetrahedra, that the tensile resonance that would be inherent in a structure like that would be like the string of a guitar or the string of a piano. It would just want to ring, you know what I mean? It's kind of in its nature. And certainly if you actually take a crystal star tetrahedron and bash it with a hammer, you can actually measure double toroidal electrical fields, electromagnetic fields pulsing off of the crystal because of this kind of internodal geometrical interrelationship between all of the angles and the lines and the facets. Whew, blimey. So you can see how a simple mechanic from Hornchurch could entirely fry his brains trying to delve the depths of this, so I'm going to refer back to Stephen Wolfram for probably, if not a summation, then certainly this is kind of this is what it's about. This is a new kind of science, and like I said, I don't base all of my stuff on Stephen Wolfram's work at all. It's Buckminster Fuller and numerous other minds on the subject. So, but it seems that many scientists are stumbling on this work and not really quite grasping the significance of what it is that they're finding. Anyway, so here's a new kind of science.
Actually, what I want to do is to tell you about sort of an intellectual structure that I've spent the better part of the past 20 years building. And I think it's a structure that has some pretty exciting implications, both now and fairly far into the future. Well, back in the late 1970s, I was a young physicist, mostly working on particle physics, but I also did a certain amount of work on cosmology. And from that, I got interested in the question of how structures emerge in our universe, from galaxies on down. Looking at that question, I quickly realized that it was actually an instance of a much more general question, sort of how does anything complicated get produced in nature? Well, there are lots of everyday examples: snowflakes, turbulent fluid flows, forms of plants and animals, lots of others. My first assumption was that with all the sort of sophisticated math that I knew from particle physics and so on, I'd easily be able to figure out what was going on with these kind of ordinary everyday systems. When I actually tried to do it, though, it just didn't seem to work, and gradually I started thinking that perhaps there might be a fundamental problem with the whole approach that I was using. Well, if one looks at history, the idea of using math and mathematical equations to understand nature has been sort of a defining feature of the exact sciences for perhaps 300 years. And certainly it worked out extremely well for Newton and friends in figuring out orbits of comets, and for lots and lots of things since then. But when the behavior one's looking at is more complicated, it just doesn't seem to work so well. Gradually, what I began to think was that was actually why there had never really been a good theory for complicated processes in nature, in physics, and particularly in biology and so on. And I got to wondering whether there might somehow be a way to go beyond the usual paradigm of thinking about mathematical equations in thinking about nature. Well, that was around 1981. And it so happened that at that time I had just spent time developing a big software system called SMP that was in some ways a forerunner of Mathematica. And at the core of SMP was a computer language. And what I'd done to design that language was somehow to try to think about all the computations that people might want to do, and then to try to identify primitives that could be strung together to build up those computations. Well, that had worked out fairly well, and in fact in a much evolved form, I think it's now worked out spectacularly well in Mathematica. But anyway, back in 1981, I had the idea that perhaps just as I'd been able to find primitives for computations people want to do, I might somehow also be able to find primitives for what nature does. And the crucial thing that I realized is that those primitives don't have to be based only on traditional mathematical constructs. I mean, if one's going to be able to do theoretical science, one has to assume that nature follows some kind of definite rules. But why do those rules involve only the kinds of constructs that have been invented in human mathematics, things like numbers and exponentials, calculus, and so on? Can't the rules somehow be more general? Well, in the past, there wouldn't really have been any systematic way to think about such things. But now we have computers whose programs in effect implement arbitrarily general rules. And the idea I had was that perhaps the kinds of rules that can be embodied in programs might actually be what nature is using. So what sorts of programs might be relevant? Well, from knowing about mathematical things, I'd assumed they have to be at least somewhat complicated. But still, I figured I should at least start by looking at really simple programs. So in practical computing, we're used to fairly long and complicated programs that are specifically set up for particular tasks. But what I wanted to know about were really simple, short programs, say ones just chosen at random. So what do programs like that do? It's sort of the simplest possible computer experiment. You run the simplest programs and see how they behave. Well, back in 1981, I came up with particular kinds of programs to try that are known as cellular automata. So here's how a simple cellular automaton works. Cells, each either black or white. Then the cellular automaton evolves down the page with the color of each cell on each step being determined by a definite rule from the color of the cell and its neighbors on the step before. Well, in this particular case, the rule is really simple. It just says that a cell will be black whenever it or its neighbors were black on the row before. And what happens is just that we get a simple uniform black pattern. Well, we can use that icon at the bottom there to represent the rule, the program that we're using. So what happens if we change the rule a bit? Well, now instead of getting just a uniform black pattern, we get a checkerboard. So far, none of this is terribly surprising. We're using very simple rules, we're getting simple patterns out. Okay, let's try another rule. It's the same setup as before, but what's going on here? We don't seem to be getting any kind of simple repeating pattern. Let's run it a bit longer. It gets pretty intricate. We can see, though, that it's very regular. It's just a self-similar or fractal pattern just formed from identical nested pieces. Well, one might think that if one has a simple rule and one starts from just a single black cell, then one would always have to get a pattern that's somehow very regular like this. At least back in 1982, that's what I assumed was true. But one day I decided to try a very systematic experiment and just run every single one of the 256 possible simplest cellular automaton rules. So when I got to rule number 30, this is what I saw. So what's going on here? Well, let's run it some more. Well, there's a bit of regularity over there on the left, but otherwise this looks really complicated, actually kind of random. Well, when I first saw this, I thought it might just be a problem with our visual system, that really there were regularities, but we just couldn't see them. So I ran all sorts of elaborate mathematical and statistical tests, and what I found was that no, so far as I could tell, something like the center column of cells here really was perfectly random. Well, this is rather amazing. We have a very simple rule. We're starting off from a single black cell, but what we're getting out is an incredibly complicated pattern. It seems in many ways random. So it just doesn't seem right. We put so little in, yet we're getting so much out. It's not what our ordinary intuition says should happen. I mean, in our everyday experience, and say in doing engineering,